Dr. Bing is an accomplished researcher and assistant professor in the Automotive Engineering Department at Clemson University. He is a renowned expert in the field of spatial artificial intelligence and has contributed extensively to the development of autonomous systems and mapping technologies. His work has been recognized with numerous awards and honors. At the AI Summit, Dr. Lee shared his expertise on the topic of spatial AI for autonomous perception and mapping. Spatial AI for autonomous perception and mapping is an important topic because it addresses one of the critical challenges in the development of autonomous systems. That is, the ability to accurately perceive and understand the environment in which they operate. Spatial AI refers to the ability of machines to understand spatial relationships and the patterns in data. When applied to autonomous systems, spatial AI enables them to accurately perceive and navigate the physical world around them, making them safer and more efficient. The ability to create accurate and up-to-date maps is also an essential for the development of autonomous systems, particularly in the transportation industry, where self-driving vehicles must be able to navigate complex and ever-changing road networks. Therefore, the spatial AI has the potential to revolutionize various industries, including transportation, agriculture, and logistics, by enabling the development of more advanced and reliable autonomous systems. Understanding the latest development in spatial AI for autonomous perception and mapping is essential for anyone interested in the future of autonomous systems and their potential impact on society. So let's welcome Dr. Lee.
Okay, Harry. Hello, colleagues and students. It has been a very fascinating adventure for me in the past few years in CUI car since I joined work on autonomous perception and mapping. With the, in the past decades, as we see, a lot of the things in perception, or even nowadays, everybody, I would say, probably you should have heard about ChatGPT, for example. So at Auto AI Lab over here, my group has been working on some of the fundamental problems in 3D spatial perception and the mapping for autonomous problems in some of the application like assistive mobility, off-road autonomy, driving safety. And today I'll take the opportunity to show you some of the fundamental research, a few of the specific as an example to show you what kind of problems is over there, what kind of problems I've been thinking about in terms of the spatial AI. So this is a picture. The first year when I was writing a proposal, I tried to envision about what happened to the autonomous perception. As we know, we just combine all of the information. That is how human intelligent creatures is able to do, to naturally just combine everything together for decision making. However, in the robotics, driving all of these scenarios, something is not naturally just happening from the end to end. And one of the first steps I've been started is to thinking about how to represent the information from layer to layer, from the sensor, from the raw to something like contextual, something symbolic. Because all of these, what I see is a way to, from the, 3D dynamic environment towards the ultimately autonomous AI, some of the concerns like usabilities, how to better to interact with the human through AI, and explainability. Everybody talking about that, how AI, especially in autonomy context, that's critical for the safety, and also about from the perception perspective, how perception work can be better to ensure the safety for some of the attacks, for example. And the spatial AI is some of the research gap between the environment understanding representation In terms of representation, we know like a 3D mesh, occupancy, yeah, make good sense. But sometimes even it can be implicit representations. Whatever, like from the deep learning to encode something as a representation, 2D or 3D, and then finally, it can be in different kind of downstreaming tasks to enable some of the 3D recognition understanding tasks. Specifically today, I'm going to introduce three of the research, starting from the fundamental geometric learning on the dynamic. And then I'm going to talking about the 3D reconstruction and the 3D SLAM. SLAM is about the simultaneously localization and mapping. So basically how to build a representation of the environment for high-level planning navigation. Finally, I've been working on the visual language navigation. Yes, language. Nowadays, language model is not something only for human interaction, actually, but it's something like in the whole framework of the AI. So language as a modality play a very critical role for the future learning, and even some of the, for example, how to leverage on the multimodality, including the language. In this case, I've been looking into some of these, some of the problems inside of the visual language navigation in the AI framework. Some of the techniques I've been looking into, certainly from the geometry perspective, supervised semantic, from the understanding of segmentation or detection, some of these problems, semi-supervised, specifically, basically how to improve the data efficiency. For example, the 3D, 2D, a lot of the work in 2D, how to leverage on the 2D for the 3D tasks, how to learn 3D with 2D. Also self-supervised. So basically, yeah, so that is the first work I'm going to introduce about how to leverage on the multimodality information for the self-supervised learning for some of the geometric learning. And on this path, specifically, I've been looking into the multimodality methodologies, how to leverage on the multimodality, some of these like a consistency between multimodality for semi-supervised learning, self-supervised learning. About the geometric learning, the research problem is in the beginning, I was trying to understand better about how deep learning with a success on image recognition, how it works for geometric problems. So one of the main concerns, certainly people has been using supervised approach, but typically the drawbacks in our case, if the data is trained in one scenario, but you have another data set, that's about the AI generalization problems, right? And also another case, supervised, always you need to have the data. And so that is one of the main concerns. So needs me to thinking about how semi-supervised and also especially self-supervised works for geometric learning, because naturally the consistency between the continuous space and the temporal, it makes sense to use that information to train for a certain in situ data set instead of just relying on general data set. And dynamic, conventionally, that is a chicken egg problem. People, if it's dynamic, how are you going to detect? And then also the information you are relying on to determine whether it is dynamic or not. So basically, it's a chicken egg problem. So how to address all of these in the geometric learning. The first work we have been working on is about the self-supervised molecular deep learning to leverage on the latter. So molecular 3D reconstruction, 3D depth learning have the problem first is there's a scale ambiguity. And also it has a relatively lower, naturally the vision it suffers from the distance, the accuracy, and how if there's a multimodality, how to leverage on the sparse ladder information to improve. Sometimes one of the things is it feels like it makes sense to fuse, but how to fuse? So we proposed a camera fusion network to advance this depth learning. So this is the network we designed. It's a two-stage. On the left stage, basically, it's going to be something based on the continuous frame, and then to formulate the photometric loss. It sounds like from the frame to the next frame, there's something consistency. So we try to train everything, including the matching, for example, and also like the pose. Everything is trained in such a framework of the to predict a certain depth, and the predict is gonna be reproject back with a previous frame to formulate the photometric loss, so the network is able to train. And the stage 2 to improve. Conventionally, there are some of the optimization problems. Basically, you're trying to optimize the depths based on some of the observation. So we try to essentially it's about the problem of optimization, and it is iteration, computing, and especially for the real-time application, that might not be a good idea. So we try to train everything, a network, to handle the optimization model using a refined network. Through this way, basically, if you see over here, this is a training step, and everything over here is only for the inference. So the inference part can be smaller, so it's going to be more computing efficiency. This is the result. Basically, the multimodality input with predicted depth. This is a projected point cloud with a color. So we achieve the state of the art for the depth prediction in the typical autonomous driving dataset called Kitty. And this is a detection result. And then to handle the dynamics, basically dynamic is going to cause the mismatch occlusion problems. And over here, so we propose the dynamic depth network is try to solve the problem to discover the inconsistency for the occlusion areas. This is a network. A few of the innovation is to design the dynamic object motion disentangle model and have a new consistent training scheme and design the 3D occlusion aware cost volume for the network training. This is the result and the visualization showing our result, especially for the dynamic areas. Another work is about the neural reconstruction. Traditionally, there are some of the drawbacks. I just used the 2D image feature for the 3D reconstruction. So we proposed the first 3D geometric feature representation we call the CV recon. The idea is we try to have based on the cost of volume, we try to represent the 3D geometric features and then finally represent the new idea of the rate compensation, contextual representation compensation into the cost of volume. We achieved the state of the art result in a 3D mesh reconstruction in one of the data set. This is about using the learning-based approach for the 3D reconstruction for the LiDAR data. About the off-road, so this is one of the LiDAR slam result we have been working on for the outside of the deep orange. Basically working on the 3D LiDAR and to improve the 3D LiDAR odometry to get the 3D point cloud occupancy maps. Okay, this is one of the projects I'm working on for the mapping for the off-road scenarios. So basically, we have been working on a few research gaps about the representation, about how to handle geometric schematics, about the soil moisture, and also about some of the network to how to fuse both high resolution, low resolution to improve the prediction result. This is some of the thematic segmentation for the terrain off-road environment. This is some of the work we've been working on for the milliwave radar for the terrain moisture prediction. So move on, basically for the visual language navigation, we have been working on input the language and then to predict the path. So this is the methodologies. We train some of the visual language navigation agent. Ultimately, the goal is to give the language input the global graph and finally to output the graph path instead of relying on any search algorithm. This is some of the result. Basically shows the effectiveness of the methodologies. This is some of the reveals some of the scientific problems like how different kind of instruction style and the navigation apps, how they can affect the model performance. So next step in the area of the autonomous AI. So looking forward to collaborate with our colleagues for new research. Thank you.